Welcome. So, today we are going to discuss about one of these deep convolutional neural networks called as AlexNet, which actually brought in the biggest amount of change and brought in deep learning onto the buzzword. So, it is roughly about a decade or close to a decade old, and this network, as it goes down, this was one of the first versions of a convolutional neural network which was brought in to solve practical problems and practical image recognition problems. So, one of the challenges which was faced on by the community and which sort of became a standardization contest across all of them in computer vision was to do a large scale image object recognition, and that is also called as the ImageNet challenge. So, it consists of 1000 object classes, and these images which are used on the ImageNet are no more of small patch size of say 32 cross 32, but these images are now of a larger size, and that is 224 cross 224 into, and that is color images. So, there are 3 channels over there. But anyways, if you look down between your standard CFAR like images which were 32 cross 32, and then you compare it with to these images over here which are 224 cross 224. So, there is a 8-fold increase across each axis itself, and that would map down to almost like 64 times or 70 times or even more of the area increase over there. So, the amount of information which you have contained in this image is much larger than the amount of information which you had in the images which are solved in the earlier case, and these 224 cross 224 sized images are what have proven down and have paved the way for these deep convolutional neural networks to actually come and be part of the world. So, we are going to start with the first model, and that is called as AlexNet. We have already discussed about it in the lecture theory over there. So, today what I am going to do is just walk you through the code and then get it started and running. Okay. So, the first part of it is just to load up all the libraries which we need over here, and the next part is to get into my data. Now, for the purpose of just for the sake of similarity and keeping it easier, I am just going to stick down to using my CFAR data. However, you need to keep one thing in mind, that AlexNet over there is going to take larger size images and not 32 cross 32. So, we need some way of converting all of these 32 cross 32 into larger size images of 224 cross 224, and for that purpose we are just going to use an interpolation later down over here. Now, what we do for that is we also need to define down whether we are going to put down some sort of a transform over there, and this transform which we take down within our test loader is going to help me actually get down an image which is of a designed size, whatever size I have designed over there, and the size which I design over here is to get down a 224 cross 224 sized image coming down over there. Now, I load down batches in batch size of 512, and that is for our similarity and consistency purposes. So, let us load down all my training and the test data in terms of using just my data loader as I had done. So, since I have my CFAR 10 data set already downloaded over there, so I can do it. However, there is another interesting part which comes down, because you have just 10 classes of objects in CFAR, whereas ImageNet was typically what is defined down for 1000 classes. So, what do we do is quite interesting. Okay. Next, let us just look into what is the size of these. So, I have 50,000 images on my training set, and I have 10,000 images on my testing set from CFAR. Okay, great. Okay. Now, there is an interesting part over there that we might not need to actually define down the whole network AlexNet from scratch. Okay. What we can do is we can make use of the predefined models which are already available within my Lua within my PyTorch libraries over there. So, once I get down over here, you would see that I have actually used this particular library from my Torch Vision. So, I have called down models which are pre-trained models which are available down, and that is within my library called as Torch Vision, and this helps me to call down any architecture which is already defined over the web. So, what we do is just we say that my network is actually AlexNet which is residing on my models, it is there. So, I am just saved down from the pane of writing down the architecture and the forward pass function over there. Now, what I do is I just take a print in order to see whether that is what exactly I was looking down for. So, you remember from your AlexNet things that what you had was that the first convolution layer is what takes in a color image over there and has 64 channels to produce down the output. The kernel size on the first convolution layer is 11 cross 11. You have a stride of 4,4, so it hops by a factor of 4, and you have a padding of 2 available over there. Then the transfer function over there is a ReLU. Following that, you have a max pool operation which has a pooling size of 3 cross 3 in which it's going to pool and pool with a stride of 2,2. So these are very different from any of the earlier networks or even LeNet which we had seen, where you were just striding down on the pooling by the same factor which was the size of the kernel for your max pooling operations. So that's quite different from the earlier one. Next, what we have is we connect down 64 channels on my output from the first convolution layer onto 192 channels over there, and then my kernel size changes. It comes down to 5,5, 5 cross 5 kernels. I take a lower stride and actually a fully connected stride over there. So I don't actually hop down while trying to do these convolutions. I am just sticking down to 1,1 stride over there with a padding of 2,2, and this is just to ensure that my boundaries and my sizes are quite consistent on what comes down. So then I have my ReLU, and then following that I have a max pool, and this max pool also replicates the same behavior of this max pooling which I had in the earlier case. Okay. Now following that I put down my convolution kernel, which converts on 192 channels onto 384 channels, and the kernel size is 3 cross 3. So this reduces down from 5 cross 5 to 3 cross 3. So you had seen that the first kernels which I had were 11 cross 11, then 5 cross 5, then 3 cross 3, and you can just refer back to the earlier lecture on AlexNet in order to check this consistency with what we had done over there. So while we had also discussed like how the data would flow, what will be the size of the kernels, and what will be the size of the data following operations. So that's what's happening over here. Now a convolution thing ends over here, which is also called as the feature learning or the feature extracting, convolutional feature extractor part of my network. Following that I just have my classifiers, which are more of the sequential connections over there. So in this sequential connections, what I have is initially I have a dropout layer, okay, which has a dropout of 50% introduced over there, and then that connects on 9,216 neurons onto 4,096 neurons. So the resultant over here is basically something which is spanned over 256 channels, and in total if you look into your XY spans over there and just sum up the total number of neurons which will be uniquely available, that sum comes down to a number of 9,216. Following that I again have my ReLU as my transfer function, and then a dropout of 50%. Following that I connect down 4,096 neurons onto 4,096 neurons and a ReLU, but no more dropout, and it's just a connection from 4,096 to 1,000. Okay. It's great, looks quite nice and interesting because this is the standard AlexNet architecture which we had. However, keep one thing in mind, that we have CFAR and not ImageNet data available to us. So the labels over there, the categories which we have with us is just 10. It's not 1,000 categorical labels. So if we are trying to train a network, it will never work out. Your cost functions will just blot out. Basically, that's the problem. You don't have 1,000. You have just 10 over there. So 990 such neurons are just going to be erratically firing up, and you don't have a control over those 990 neurons for which you don't have any labels available. So you need to make a change over the network over here, and that's what we do in the next part over there. So what I try to do is basically I remove this last layer which connects on 4,096 neurons onto 1,000 neurons. So that's what has to be removed out, and from there I just need to add down another new connection of 4,096 to 10 neurons over there. Now since the network is not trained or anything, it's just randomly initialized network which is available to me. So this change also does not bring any change onto the characteristics of the network in any way. So let's just make this change and then just look through this one. So you see that this convolutional part over there for feature extraction remains the same. You have your connections coming down over here, and then I have removed out this 4,096 to 1,000 which was present over here, and then I have just introduced a connection of 4,096 neurons onto 10 neurons, and that pretty much closes my loop over here. I have my classifier part defined, and then my network is now consistent to operate down on my CFAR 10 data sets. So let's look into the total number of parameters which are present over there. So this is what we had done in the earlier case when looking at LeNet and trying to make a whole distinction of the weight space over there. Now if you look into this kind of an AlexNet over there, you see that we have something like 5 crore 70 lakh 44,810, or if you just go down by the metric system, then that's about 57 million parameters. So this is where your thousands go down, this is where your million comes into play, and then you have 57. So it's 57 into 10 power of 6 or 57 million parameters which you have to train over there. Now the network does not look complicated to most of you. However, you see that the number of parameters is really large, and then that's what happens. So in the next subsequent lectures, we will be doing even deeper networks which are called as so we'll start with VGGNet as an example over there, where you will see even more number of parameters coming down over there. So, the number of parameters is really high, and thanks to one of the points that the number of convolution kernels you are taking down at every layer, that being really large. So, the number of parameters have to be high, there is no other way of going around with that. Okay. So, that goes around it, and then what we do is we just end up copying down my weights which are the initial random initialization weights which are present over there. So, let us do that. So, at this part we are just going to copy down all my randomly initialized weights which I have over here, such that I can reuse when I am trying to look down what happens at the end of my training process. So, let us just run this part, and that is where my weights get copied down and kept down for me at the initial part of it, and then later on after the training process we are going to make use of them for visualization purposes. Now, the next part comes down where I just see if my GPU is available. Since if GPU is available, then I can just make use of my GPU coming down over there. So, it just waits on for the polling to happen down. If it comes out, yeah, so my GPU gets detected and it is available, and I am quite set down to run on this one. Now, for this to be a classification network, what I am going to do is my loss over here is no more MSE or any of them, but it is just a classification loss, and I am going to make use of negative log likelihood cost function over there. The optimizer which I make use of is Adam, and that is based on our historical evidence and the earlier lectures where we had actually polled across a space of optimizers and to find out which of them is the best possible optimizer to work on. So, we run this part and that is done, and then I get into my training. Now, since this network does take a bit of time to train, I will just set this one running while we keep on discussing about what goes down inside the network. Okay. So, now if you look through this training procedure, I am just using 5 iterations for it, and that is just for the sake of sticking down to our time limits over there and not just overshoot it out. Now, if you have enough of time, and in fact, like when you are doing it on your own side, I would tell you that keep on training it now. And if you want to really look into what an AlexNet, how long it would take, you are suggested that you actually train it down for more than 10,000 number of epochs and use an actual ImageNet kind of data in order to do it, and not just stick down to CFAR network coming down. So, within my training system over here, I have my epochs which goes down. Within the epochs, what I do is just find out if my GPU is available, then convert it onto a GPU availability, and then have my inputs available over here. Now, my input is both the image which comes down as well as the categorical label over there for whatever class is getting defined, and then for since I have 10 classes over here, so it is 10 classes which are present down in my label. Now, what I do is zero down my gradients whichever is present inside over there, do a feed forward over the network, and then find out my loss. And the loss over here is computed after a log softmax over my whole transfer function and the output, and convert it down to my labels which I have over here. Now, once I get down my loss, as in the loss of classification at the end of each epoch, I am just going to find out what is the derivative of that loss, or that is a nabla of the loss function. Okay. Once that is done, we run down our step function, which is to do one step of a back propagation across the whole network over there. So, that is going to propagate across my fully connected and my convolutional connection layers over there completely. And then I accumulate my losses over the whole patch which has been coming down, finally coming down to getting an average training loss for each epoch, and then I just create an array of these training losses to look down what happens across all the 5 of them. Now, once I have done my training over there using my training data, the next is to actually look down into the performance validation. Now, for that I am going to make use of the earlier case, which was just with 10,000 images on my testing data set and how good it performs on each of them. So, what I do is initially load down my inputs over there from my test loader, and once I have my inputs available, I do a feed forward pass over my network and then get down my predicted value coming down over here. Now, this prediction over here is not the value, but that is the index label over there of whichever has the maximum value stored over there, or the maximum probability. And then if your value matches down the exact label over there, then it is correct, otherwise it is wrong. And then since you had 10,000 such images or 10,000 samples in your test data set, so the average accuracy is the total number of corrects divided by 10,000, and that gives you the total number of correct measures on average which has been made down. So, once that is done, I have my average accuracy for testing case taken down, and then over here I have my same old repetitive plotting functions which can be used for plotting down my cost functions while I am training on the training data set, as well as looking down on my accuracy which keeps on increasing expectedly, which is supposed to increase down as I am training it across the number of epochs over there. And finally, to print out what comes over here. So now that we have kept on running this part of the trainer, and then we have seen what the trainer consists of. So let's have a look into how it has trained out over there. So if you look over here, we have just trained it for just 2 iterations, and for the sake of time, it takes quite a long amount of time, and that given down that your AlexNet which you have over here, that has a significant number of convolutions which come down, and then your fully connected layer, and that makes it really complicated to work it out. So here when I have this trained down, you see that there hasn't been much of a change over the loss, but then and then as well as the accuracy has not increased. But given the fact that this is a very deep network which you are going to train, it will take a more amount of time in order to do that, but the final convergence accuracies are expected to be much better than what you had with lesser number of neurons along the depth. So because when you have a network which is much shallower, not with so many number of neurons over there, so the total number of trainable parameters is also less. The lesser the number of parameters, it's much easier and faster to train it. However, the hierarchical complexity in which it can encode data with lesser number of parameters is much lower than what it would need for encoding for a deeper number of network. So if you have a deeper network, since you have more number of parameters over there, so the effective space of features and their hierarchical representations which you are learning is much higher, and in that way the total saturation accuracy increases. So you would need longer and longer to train over for a deeper network, but then the final performance always is something which is to be amazed, and it's remarkable. So let's have a look into what happens down with the loss function. So the loss function as such is still decreasing. It has just operated on 2 epochs, and it's just a start of it. So in general, I would suggest that keep on operating it over for at least 1,000 epochs. That might take time, and for the given the kind of a high power GPU which we have, it already took us more than a minute. So if you're running it on a CPU, then you have to sort of bear with it and keep on running for a longer duration of time. So though the accuracy has not changed as much over there, and that's for a marginal change which has happened, but then let's look into what happens down with the weights over there. So what I have done over here is quite similar to as in the earlier case, that after my training I just copy down my weights and then try to visualize out my weights over here. So when I go down to my weights, these are my first convolution layer. So my first convolution layer basically has 1, 2, 3, 4, 5, 6, 7, 8, that is 64 number of kernels over there, which are arranged in a stack of 8 rows and 8 number of columns per row over there, and each of this is an 11 cross 11 matrix. So let's count it out: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and on this side you have 11. So it's a 11 cross 11 and maps down a 3 channel input onto these weights, and that's why you have a color thing coming down over there. So going by the same logic, this is what was the initialization, the random initialization of my network which I had, and these are the weights which comes down after my training. Now you don't see any features as such coming down, and to be very frank on that, there hasn't been any possible large amount of learning which has happened over there. It's just been from my random to what is after 2 epochs over there. So if I look down into my difference, you do see that some of the weights are changing because there is a significant amount of differences in the weights which are coming down over there, and then this is an indicator that the learning is happening, and then you are not hitting down on a valley region or a saddle out point, though your accuracy gives an indicator as if it's just stuck down at 10%, but then the change which is happening over here is much lower. So this was about the first layer which you had. Then you have the second layer. In the second layer, what you do connect down is that you take down this 64 channel input over there and connect it down to 128 channels. Okay, and then these 64. So if we take any one of these kernels of the second convolution layer, so it has 64 such 2D matrices which constitute the whole kernel over there. So my second convolution kernel, which is a 5 cross 5 in spatial spread, has the z axis or the total number of channels over there, which is equal to 64. So what I do is I pull out one of these kernels and display all of these 64 such 5 cross 5 matrices over there. So this is what constitutes for one of them. So if you can look over here, it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's the 5 cross 5 matrix, and there are 1, 2, 3, 4, 5, 6, 7, 8 of them, and arranged 8 of those rows as well. So that makes it a whole collection of 64 kernels coming down over there. Now these were the kernels weights which were before the training. This is what happens after this training procedure of 2 epochs, and if we look down at the updates which comes down over here, you see that there has been some change even in the second place, though some of them haven't changed at all. If you look down over here, this is practically 0. These are the ones which have ideally, like all the weights have made that much of a positive change. This is where all the weights have made significant amount of a negative change as well, and some of them are randomly changing, some of them have directional changes as you see over here. Some of them are like this. So, this is just to give you an indication of how these changes are happening, and that the whole network is training down over there as well. So, this was one of the first kind of a deep convolutional neural network for a practical application using large size images. So, the subsequent ones which we do will now be looking into those larger size images of 224 cross 224, and then how to work around with them. And to give you a word of advice over there, so if you have access to higher performance computing over there or cloud access in some sort, then please try to use it. Please try to use a GPU if you have some resource available, or if you are trying to run it on a laptop or standard desktop CPUs, then please bear on and give it some time, though it will not be blasting off your memory, but it would just be taking a tad bit longer to work it out. Then that's what you have to do given the number of calculations and the number of parameters you are training. So with that, keep on stay tuned and stay excited as we go on to the next version of even deeper networks.